is Dr. Nicolas McMorris. I'm the chair of this session on energy and materials. We are going to begin this session with Mr. Alton Daly, who's going to be presenting a paper on in-depth investigation into Jamaica's wave energy resources using buoy, altimetric, and model data. Mr. Daly.
All right, so good afternoon, everyone. Can everyone hear me clearly? All right. So as Dr. McMorris said, I'll be presenting to you on an in-depth investigation Good afternoon. So as introduced, my name is Alton Daly, and I will be presenting on an in-depth investigation into Jamaica's wave energy resources using buoy, altimetric, and model data. Now, this research is done in collaboration with the Climate Studies Group, MONA, and the Caribbean Geophysical and Numerical Research Group from the French West Indies. Now, why are we doing this study, right? Climate change has urged us that we need to be better able to manage our coastal areas, right? Which means that we need to be better able to manage our wave parameters, which include stuff like significant wave height, wave period. We need to do better investigation where that is concerned, right? Reason being, sea level variations has been unstable, and sea and our beaches is one of our main drivers of our economy. It's what we depend on a lot, right? We depend on it for tourism. It's what people come here to actually benefit from, right? So what we are proposing is that waves can actually be used. We can actually harness the energy from the waves, right? Now, why wave energy? What is so significant about wave energy? Now, the thing with wave energy is if we harness the energy from the waves, it serves both a dual purpose. We can actually harness the energy as well as we can actually use the wave energy converters as coastal protectors, right? So generally what happens is after the waves actually hit the wave energy converters, what we have is a reduction of energy on the lee side of the wave energy converters, right? So it serves a dual purpose. We extract the energy as well as we use it to actually reduce the coastal erosion. Now, in order for this study to be successful, we need to take a look at statistical values for the parameters that I mentioned previously. We need to develop a better understanding of the dynamics of the resource in the coastal areas. We need to assess the extreme conditions, which include hurricanes, tropical storms, and we need to be able to model the energy conversion. Now, our study area is just 300 kilometers off the coast of Jamaica. So it's within that region there. It's within that region here, right? Now, based on the figure there, you can see that Jamaica basically has access to deep sea water from two locations. One is through the Cayman Trench, which is here, where we have the microplate of Gonav, where the depth is approximately 7,000 meters, and the other is to the southeast through the Caribbean Sea here. All right? Now, also, it should be mentioned that within this area, the temperatures and the salinity experience seasonal variability. However, for the water currents, there's not much variability in this location. Also, Jamaica has approximately 1,000 kilometers of coastline. However, even though we have this much coastline, one of the issues that we have is that Jamaica is a narrow band, which means it's susceptible to sea level rise. So how do we plan to conduct this experiment? So we have three basic models here. We have WaveWatch 3, we have SWAN, and we have SWASH. Now each of them performs a different function. Now WaveWatch 3 allows us to do propagation in deep sea conditions. SWAN allows us to do propagation in coastal environments, and we use an unstructured mesh. Reason being, in the coastal environments, we find that it's a bit more complex. The environment is a bit more complex than in deep sea conditions, right? And SWASH gives us the ability to look at the dynamics of the resources. So we look at stuff like the water level, we look at the water current, the wave speed, the direction from this model. And all models that we used are forced using numerical data, right, that we observe, that we extract from the weather model, weather monitoring systems, and ocean model and ocean monitoring systems. Now this is a small run of one of the models. this is a simulation showing significant wave heights that we observed at Morant Bay and I think it's Morant Point, right? So what happens here is we provide the model with boundary wave data, bathymetric data, wind data, and ocean current data. And what we get is we get a result showing significant wave height, we get wave period, we also get stuff like wave direction, wind direction. But this is just a small run because we recently started the modeling. Now in our preliminary research, what we did was we gathered data from 3 different sources. We gathered data from buoys, right, which is monitored by NOAA, the NDBC, and they have a small network of buoys around Jamaica. We have two buoys surrounding Jamaica. And what we found is that we got significant wave heights, average significant wave heights of 1.90 meters in one location and 1.27 meters in another location, and periods of less than 7.35 seconds. Now the issue with these buoys is that, as I said before, it's only 2 that's around Jamaica. So the buoy density around Jamaica is very low. We don't have as much. So what we did is that we substitute the areas that were missing with altimetric data. So we use data from satellites in order to cover the areas that we didn't have the necessary measurements being taken. Right? So we did a spatial averaging of the significant wave height. The satellite data doesn't necessarily provide information in terms of wave period, direction, that sort of stuff. It's just the wind speed and the wave height. Right? Also, there's another model, another source of data that we use from NCEP, where they run their own sort of models, and what they do is they provide us with information regarding the significant wave height, wave period, wave direction, wind speed, and wind direction. Now, the benefit with this source of data is that it allows us to do some sort of statistical downscaling. Right, and it allows us to investigate the symmetry of the variable that we are investigating. Now you might ask, how does wave energy converters work? Right? Wave energy converters, they basically take advantage of the horizontal and vertical motion of the waves. And there's also another device where they basically collect the water in like a tank, and they run the water through turbines, which generates the necessary electricity. Right? In our case, there is one wave energy converter that would be suitable for our conditions, which is the Wave Dragon. It's an overtopping device. Right? It's the device that I described last, where the water basically runs over, it's collected, and then it runs through turbines. Right? But the issue with this converter is that it only has an efficiency of 40%. Right? So in terms of significant wave height, based on the values that we've found, we have a result here that shows that we can only produce 1.9 to 15 kilowatts per meter of power, right, which would be equivalent to 1.5 to 15 inhabitants per meter of wave converter. Now here we have a spatial plot. So we're showing here how the significant wave height varies going from east to west. Right? But this is only the 3 buoys that are surrounded, that are within proximity to Jamaica. And what we find is that going from east to west, we find that the significant wave heights are decreasing. Right? And then what we did after is that we filled the gaps with information from the simulation done by NOAA, as well as the data from the satellites in order to complete the plot to get a better picture of what's going on around the country. And we still see here that going from east to west, the significant wave heights are decreasing. Now you might ask why. Now if you look here, our wind speeds also going from east to west, they're also decreasing, and majority of the waves that we experience here are wind waves, so they are generated based on winds, right? So I should also mention that the Caribbean Sea is semi-closed, which means that the waves, the ocean swells are not allowed enough room to develop and move towards the coastline of Jamaica. So you find also that moving from east to west, that's another reason why the values are decreasing. Now in terms of production, the months of July and June would be best for production. Also December and January. However, September and October is not so good for production. Now in concluding, we say that wave energy potential, it's low. Despite it being low, there's still some possibility to actually harness or to use the energy from the waves. So that the environmental conditions are relatively stable. Natural risk, it's medium. The data available, it's enough to assess the resources. And the data on the coast, it's non-existent, there's none there, which is the next step in the research process. So we're going to use the model SWAN to help us to actually get data on the coast. Predictability of the resource, we need a specific model. So the combination of the three models that I proposed earlier will be our model that we use in order to characterize our resources. As you said, it's in progress, and the climate change impacts, they are non-negligible. So we cannot ignore them. All right, and finally, wrapping it up, exploitation is possible in a cogeneration configuration, meaning wave energy project can be a good opportunity to investigate the coastal area in order to face future modifications of the climate. However, effort must be placed on economic feasibility, improvement of the numerical tools, and real-time observation. And my focus here is the improvement of the numerical tools. All right. Thank you for your attention.
Thank you, Mr. Daly. Any questions?
It's not a question, but a comment. Are you aware of the global sea level monitoring network?
No.
Because Jamaica has 2 tide gauges currently.
Yeah, but tide.
Would that help any
No.
at all? Okay.
No.
All right. Thank you, Mr. Daly, for your presentation. Quite enlightening.
All right, thank you.
All right. So next we're going to have Mr. Craig Rattray, who's going to talk us through a paper on the novel low-cost image-based solar tracker via maximum intensity mapping. Mr. Rattray is just getting ready with his headset and his mic here.
Good afternoon, everyone. Can you hear me clearly? Okay. Okay, I was introduced earlier. I'm Craig Rattray, and I'll be just explaining some work I've been doing on a novel low-cost image-based solar tracker via maximum intensity mapping. And as you might imagine, it's just taking some pictures, analyzing the pictures, using from what you would have what I have analyzed. I would determine, at least identify the sun, and from identifying the sun, determining its position, and running that information through a Python program that I've developed to align for maximum extraction or generation from solar PV systems. My supervisors are Dr. Kurt Edward and Dr. Ferret. Oh, this thing is not, all right, never mind. Okay, so my rationale, as you imagine, whenever you are stepping into a direction, especially for developing countries, one of the main things that like we always think about is sustainability and cost. And my rationale was just to think about sustainability. Solar PV systems, they are not as efficient as we would want them to be. And the JPSCO suffers somewhat because of the maybe you could call it erratic behavior. We have a cloud cover coming over on a system, and your production plummets, and it creates some stability issues. So my plan is to try and make some impact in that regard. I will also be sharing with you some of the research methodologies that I've seen. I'll be looking at the advantages, limitations, and after going through that, I will show what my approach was. And I will give some indicative achievements and some of the limitations from that. Now, for those who don't know exactly what's the principle behind a solar PV system or how it works, for maximum output, you would want to have the light, the incident angle being basically 0, which means that the light must be hitting the panel, face of the panel at 90 degrees. The picture that they're showing you in red, there are actually two possible ways of doing it. Looking at it horizontally, which is shown in blue, if you can see clearly, and in red, you're looking at it vertically. So essentially, you have two ways of tracking. You can have vertical tracking, or you have horizontal. Now, in terms of the benefits, I've shown just some outputs that I've seen presented by our scientist, and what he is indicating is that for 2-axis, when you do both vertical and horizontal tracking together, you're able to get maybe somewhere in the region of 30 to 50% more generation than you would if you had a fixed panel, which is predominantly what we have in Jamaica. I would want to see some changes with that. If you're tracking only single axis, then you can get 15 to 25%. On average, though, which is interesting, you can get up to 30% more power output from your system, which means that on a given day, you can start using your system much sooner. You have more practical power coming out much sooner than if you had another system, which is what we are seeing. Now, moving into the sun position sensing methods, I came across 2 methods. The brightest region method, which is basically, as I said, you take a picture and look for the brightest spot. And a picture there that you're seeing is just one of those that I took, just to show the sun is the brightest spot. And there is also this other method, the shape detection method, which is basically creating a binary image of the picture that you would have had. This is an inverted binary image. So if it was just a binary image, that black spot would be white and the entire screen would be black around it. I've inverted it just to make it clearer. That spot right there is the sun. And there are some work where persons actually look at the shape. It's circular. And that's what they've written algorithms to track that circular shape. Now, looking at the sun position sensing, that's the brightest region method that I just mentioned. The fundamental principle is the same as what I'm using, maximum intensity mapping, which is the brightest spot. Now, the advantage of this is that you can track errors for less. Tracking errors is less than 0.1%, which is very good. It's 0.1 degree, almost 0 incident angle, and it's achievable. And what it does is it allows you to be able to do it even if the cloud is there, which is one of the great thing about it. The limitations, though, is that errors sometimes can be made large if the cloud is there, depending on what you're doing in the program, in developing it. Now, this just to emphasize the limitation that I noticed. If you look at the first image that is to my far right, at 12:51, I took an image. Now you see the sun. Remember, we're looking at the limitation of the brightest region method. At 1:06, because of cloud coverage, the brightest spot shifted. By 5 minutes later, at 1:11, the point shifted. You see that little black circle? Yeah, that's where the brightest spot is. And by 1:16, there's a shift again. So if I found out now that if you were just to look at the brightest region method only without any constraints, you will have a system becoming very erratic. And you would be aligning with things that are not really the sun, and your production would have plummeted. And at 1:21, I took that picture again, only to just to show the path that it would have taken and where your system would have gone out of alignment from there. Now the next method, which is the sun position sensing method, or shape detection method, sorry. The fundamental principle is just to, I'd said it before, the detection of a shape. In this case, it's a circle. And I said also it was generated from binary images. And it's somewhat based on maximum intensity mapping as well. The advantage, once appropriate thresholds are applied and the shape of the sun is circular, accurate tracking errors can be achieved. A limitation, however, is that if clouds are close enough, then you have diffusion and the shape is no longer circular. And there you have a system that is unable to make any decisions. So that's one of the limitations. And by virtue of all the steps that are required, this process is not really it's not done in real time. First, you take an image, then you would somehow try and determine what's the threshold value that you're going to be using. And then you put it in the algorithm to determine what to do next. And this is what, just to emphasize, the shape, because of the cloud, the shape is not circular. So this is a limitation. My approach now is to determine an appropriate range of intensity values based on adjustable camera settings and use it in real time to correctly identify the sun via the brightest region method, similar to what I described earlier, and then to note the sun's position via the shape detection method without the use of histograms or binary images. I'm not looking at shape, I'm just looking at intensity values. And that will give me an advantage. And also, from the first point I made, the camera, you basically set the camera settings, choose some camera settings to determine what the intensity value that you'll be looking for. So I'm not really looking for shape, but I'm looking for a particular intensity value that is predetermined. And that I found has given me some advantage. So my research methodology is, after determining the practical range of intensity values, I developed a Python script to generate blurred grayscale images from raw images, which is one of the steps to extract the intensity values. Then identify the sun and its pixel indices in images generated. Then after that, I performed some computations to determine the required orientation for attaining low sunbeam incident angles. The computations were done at 15-minute intervals, and it was chosen because from previous works, the incident angle, we found that at 50-minute intervals, you would still have deviation of maybe around less than 5 degrees, which is minuscule in the whole scheme of things. The total output would not have been reduced in any way, really. And the final step in the methodology was to change the system orientation based on the computations. The image parameters, basically these were the camera settings that I used, and these were the range of intensity values that I obtained from it. I chose these camera settings because the range is actually from 0 to 255. Getting from 0 to 253 gives me a lot of flexibility. From the from this information, I was able to determine not just identifying the sun and determining its position, but I was able to determine from assessing the pictures what time of day it was, or determine night from day. And from that, I was able to, my achievements, acceptable sun position tracking was achieved with accuracy within margins of 1 degree under clear skies and 5 degrees under cloudy skies. I know that further work can be done to improve this, but for the sake of just the fact that we're not doing solar concentration, this is acceptable. And limitation, sunlight diffusion by clouds resulted in deviation angles exceeding the approximately 5 degree value expected. And I noticed as high as 10 degrees, which was kind of bad, but in the whole scheme of things, it was still good. Because at 10 degrees deviation, you are looking at losses less than, I think, if my memory serves me correctly, it's still under 5% reduction. And the total error includes computational errors as well, because you have to be working out how long to energize the actuator for to get the alignment that you need. So that was one source of error. And for future work, I will be looking at actually modifying an existing system. And after modifying it, I will observe how it works. And from that, I will be able to determine the cost effectiveness of the approach. And maybe looking at other ways of implementing it across the island. These are some of my references. And thank you for your attention.
Thank you, Mr. Rattray. Any questions?
Yes, good afternoon.
Yes, good afternoon.
I love the presentation.
Thank you.
What I didn't get from it is that the environmental conditions for setting up such an equipment, usually you have some sort of standard as to the surrounding conditions to set up your equipment to get the best results. Say, for instance, in meteorology, when we're setting up an AWS, there is some standards that you shouldn't have trees within, say, 20 feet of the equipment or something like that.
Yes, you're right. There are some environmental conditions that can affect a system. But in this case, I had earmarked a system that is actually currently working. And what I plan to do is there are two identical systems. My plan is to modify one and make a comparison between the two. With respect to shading and other things that may interfere with its performance, those are not in existence at the location I'm thinking. But in general, generally speaking, if you're putting in a system, you have to take all of those things into account. Shading, spacing behind the panels to ensure that it's adequately ventilated for cooling. And there are so many other things that you need to be accounted for.
Okay, thank you. Any other questions? No. Thank you, Mr. Rattray. I look forward to the implementation and development of your solar tracker.
Yeah, thanks. Yeah.
All right, so next we'll have presentation on crystal engineering and synthesis of lanthanide metal organic frameworks using conceptual tertiary building units for materials with tunable luminescence. I'm sure Mr. Zahar Min, who's going to present it, will be able to explain that to a structural engineer like myself.
Hello. Good afternoon, everybody. Thank you for the introduction. I'm grateful for this opportunity to present some of my research with you today. And this will, especially on the crystal engineering of lanthanide metal organic frameworks using some conceptual tertiary building units for materials with tunable luminescence. This will be the outline of my presentation, and I'm going to start by giving you a brief introduction on what metal organic frameworks are and what makes them interesting. So metal organic frameworks, MOFs for short, are hybrid materials made up of inorganic metal ions or metal clusters, which act as nodes and are linked together by bridging organic ligands to form multidimensional networks with cage-like or framework topologies. Hence the name metal organic framework. Right? The network connectivity of these materials tend to lead to materials with, that are often porous. As you can see here, you can have spaces and channels within the framework, and this is actually a crystal structure of a MOF with zinc oxide metal clusters with terephthalic acid linear linkers. And the yellow sphere here just shows you the pore or the space within these frameworks. Now, these materials have inherent characteristics that make them attractive materials for functional materials. For example, you have both the advantages of the organic as well as the inorganic components. And in this specific example for optoelectronic applications, you can have linker-based emission as well as metal-based emission. Furthermore, you can have interactions between the organic and inorganic components, such as charge transfer mechanisms or ligand-sensitized emission, which can enhance, or sometimes even new properties can arise due to these interactions between them. Furthermore, we can have host-guest interactions, meaning that their guest molecules can go within the pores and interact with the framework. And this, we can envisage how you could use these materials for sensing studies, for example, as different guest molecules will have different interactions with the framework and lead to uniquely identifiable signals, right? So as I said, this schematic here is just specifically for optoelectronic and sensing applications, but these core characteristics of metal organic frameworks makes them suitable for a plethora of applications, including catalysis, gas storage, magnetic separation, and purification applications. In fact, many MOFs are already commercially utilized, especially in catalytic and purification applications. And the potential for such a wide range of applications makes them very interesting. And as you can see, over the last 3 decades or so, there has been an exponential increase in MOF research, right? And continued research in these materials could significantly contribute to a number of our global goals for sustainable development, especially goals 6, 14, and 15. And hopefully, in these last couple of slides, I've created an appreciation for why these materials are so interesting. So I'd like to take you through a little bit of how these things are made. Traditionally, MOF materials are made by a serendipitous synthesis, meaning that we just get a bunch of inorganic and organic components, put them in a reaction vessel under certain experimental conditions, and just kind of hope for the best in a trial and error sort of way. However, this approach, though not ideal, was still relatively effective because many novel structures with interesting properties arose from it. However, if we could control and direct the structure and topology of these materials towards targeted specific applications, then we could truly take advantage of the potential of metal organic frameworks. And in that, over the last decade or so, there has been great progress in the crystal engineering of these materials, especially by Professor Yagi and his team, who came up with a concept called reticular synthesis. Right? Reticular synthesis now is the deliberate formation of judiciously designed rigid molecular building blocks into predetermined ordered structures. And here's an example of reticular synthesis taking place, where you can have 5 different organic linear ditopic linkers are used to make 5 different metal organic frameworks. But all 5 of these frameworks have the same network topology, meaning, and that is called, when they have this, when different MOFs have the same network topology, they're said to be isoreticular with each other. And I want you to pay attention to this word because I'm going to use it quite often in this presentation, right? So these 5 different isoreticular structures combined, you can call them as an isoreticular family, right? To utilize reticular synthesis, we need to have an understanding of the network connectivity of these materials, identify the building blocks that lead to that particular network connectivity, and be aware of the reaction conditions that will lead to the formation of these building blocks, right? And these building blocks in MOF chemistry are called secondary building units. And they are recurring conceptual fragments that act as points of extension defining geometrical shape. So here are some examples of some SBUs, and if you could just imagine where the gray atoms, if they were to extend, this SBU would extend in a square form, this SBU would extend in a trigonal form, and this SBU would extend in an octahedral form, such as in this particular case. The formation of these SBUs are predictable in transition metals because of their coordination chemistry and crystal field effects. However, this is not the case with lanthanide metals. Now, lanthanide metals are elements from 57 to 71 and are sometimes grouped together with scandium and yttrium to be known as the rare earth elements. And they have electrons in the f orbitals. Because of that electronic structure, they have a spherical crystal field, which means that ultimately that means that the formation of lanthanide secondary building units are unpredictable. And it is the predictability of these SBUs that allows for control and in the rational design of these materials. So with lanthanides, when they're not predictable, when they're unpredictable, there are many challenges with the design and synthesis of these materials. So why do we even want to try if there are such challenges? Well, simply put, lanthanides, I consider them cool materials in the sense that they have properties that are different from other elements, and such as unique optoelectronic properties, high chemical stability, and their variable coordination chemistry lead to new novel structures with uncommon and intricate structural topologies. But it is this variable coordination chemistry that also creates a challenge in the rational design of these materials. But having said that, I just want to bring back a previous slide that I have and put into context that even transition metal MOFs at a point in time could only be made by serendipitous synthesis. And it was through research by scientists like myself who decided to take on this challenge and try and find solutions to come up with crystal engineering concepts and synthetic approaches such as reticular synthesis. So having said that, the objectives of our research were first and foremost to synthesize novel lanthanide metal organic frameworks, but more importantly, to develop novel crystal engineering approaches so that we could rationally design and synthesize families of isoreticular lanthanide metal organic frameworks. And of course, in a culture dominated by industrial viability of materials, it is also important for us to investigate the properties of lanthanide frameworks for potential applications. So going into my results, I've made over nearly 30 novel compounds across 7 different structural types, but in this presentation I'll focus mainly on UWI MOF1 to MOF4, touching a little bit on some interesting properties of MOF7. So UWI MOF1 was made with a number of lanthanide metals and benzene dicarboxylic acid, which is this particular ligand here, and it formed a 3-dimensional pillared framework. As it's a 3-dimensional framework, as you can see here, the ligands are pillaring the lanthanide SBU layers. And during a routine survey of the literature, we came across a paper by Deng et al., who reported a structure which had the same molecular formula as our MOF1. The only difference being the ligand that they used was a biphenyl ethene 4,4 dicarboxylate. And so we decided to look upon closer inspection of the structure. We realized that this structure had the same network connectivity as our MOF1, meaning that the two structures were isoreticular to each other. So, and at the time, that was very, very uncommon. So we decided to study the network topology of these materials and to see if we could extract some design tools in our attempt to crystal engineering lanthanide frameworks. What we found was that they both had distorted dodecahedron coordination polyhedra, the same ligand coordination chemistry, and the same identical secondary building units. But what was interesting was that these secondary building units interconnected with each other to form a 2-dimensional sheet. And this 2-dimensional sheet layer was made up entirely only of secondary building units. So we came up with a term called tertiary building units. And you can see how the tertiary building unit layers are pillared by the organic linkers, and we hypothesized that it was the formation of these tertiary building units that was the determining factor in the reticular formation of these lanthanide frameworks. So in order to test out this hypothesis, we designed certain experiments with similar but different linear ditopic ligands, and thus we got UWI-MOF2, which was done with biphenyl dicarboxylate acid linkers. Here it has 2 rings instead of the 1 like in our first MOF1, and we were happy to find that, in fact, this was also isoreticular with the first 2 compounds, making this a third isoreticular member of the family. We're also able to do this with 2,2-bipyridine 5,5 dicarboxylate, as well as with 2,6-naphthalene dicarboxylate, making this UWI-MOF3 and MOF4 the 4th and 5th member of this isoreticular family. And we can see the tertiary building unit prevalent in all of these structures, giving us confidence that our hypothesis is correct. But of course, more examples are needed to solidify our theory. So UWI-MOF1 to UWI-MOF4, along with Deng's structure, constituted the first ever family of lanthanide metal or isoreticular, first ever family of isoreticular lanthanide metal organic frameworks using these 5 ligands. And not only were they the first ever family of isoreticular LMOFs reported, but MOF 2, 3, and 4 were the first lanthanide metal organic frameworks that were deliberately synthesized by design. And some of this work was published in European Journal of Inorganic Chemistry, which won a Best Research Publication Award back in 2013, and so far has up to like over 22 citations. Right now, before I move on, before I finish with my talk, I also want to talk a little bit about MOF7. As I previously said, this was formed a 3-dimensional intricate lanthanide metal organic framework with this hydroxyterephthalic acid ligand. And as much as I'd love to take you through the detailed structural description of this compound, I only have time to show you some of its interesting properties. Right? So with these, the europium and terbium analogs of these compounds emits red and green light, strong red and green emission. However, if we made these materials with a mixture of both europium and terbium metals, we were able to control the emission color from red to orange to yellow-green to green, depending on the relative ratios of these metals. And our photoluminescence spectra showed that they had both europium 5D0 to 7FJ transitions, as well as terbium 5D4 to 7FJ transitions. But of course, the relative intensities vary depending on the concentration, and was consistent with the emission color that we see. So, of course, we're continuing to do studies on these materials, especially in sensing. But in summary, metal organic frameworks can be exploited to yield novel functional materials. However, there are challenges associated with the rational design and synthesis of lanthanide metal organic frameworks. Despite these challenges, we have come up with a new synthetic approach using tertiary building units, and successfully implemented this design approach to form the first ever family of rationally designed isoreticular lanthanide metal organic frameworks. And lastly, a number of our MOFs have, in fact, most of our MOFs have some degree of tunability in terms of luminescence, but we have some very exciting materials with tunable luminescence properties. And for the future works, we need more examples. We need more examples of this synthetic approach being viable. So we're trying to make novel families of isoreticular MOFs using this tertiary building unit approach. And in fact, just this week, our undergraduate research student gave me some very promising results to say that we actually have successfully synthesized a second family of isoreticular lanthanide frameworks. And also we are doing some sensing studies on small metal ions and nitroaromatic explosive compounds, which my colleague Jermaine Smith will talk to you a little bit later on in this session. And with that, I would like to thank the following people and entities for their continued support. and especially to my family and my supervisor, Dr. Singh Wilmot, who has taught me not only to be a better scientist, but a better student, a better teacher, and a better person overall. And lastly, I'd like to thank you, my audience, for your attention, and I'd like to invite any questions that you may have.
Thank you, Mr. Zara.
Gosh, this looks very exciting.
Thank you.
I'm in the field, practice-based natural medicine, because I was brought in by some medical doctors who want to tap into my knowledge of genetics, molecular biology, organic chemistry. Well, molecular biology is really just the organic chemistry of the cell.
Right.
And your work there is really more into inorganic chemistry, analytical chemistry, which I did some of, but I'm more in the organics. But I'm excited by this because part of our work now, we're looking at what is called energy medicine. Everything is going to energy medicine because everything is energy. Well, I've been working at that for a long time through community health and psychiatry. Most of UWI is not aware of that. I work with this lady called Pat Desai, who is in that. But out of that, Pat's work and I, we're looking now at this future which incorporates your work in terms of frequencies, the lanthanide metallo-organic frequencies. It's exciting because people use colors to meditate and to absorb information, because radiation is really information which goes into the body and instructs the activities of the cells. So your work is very valuable because if you teamed up with the right set of doctors or natural medicine people like myself, we could probably rapidly create something that we could market in terms of software to the energy medicine people. So my question is, can you do it? You know, would that be part of your interest? The other thing is, can you increase the range? Because you're part of the rainbow spectrum, but if you could go up to the violet end, the violet frequency is awesome. And if you could do that, maybe not with the lanthanides, maybe another rare earth series, that would be terrific. You could market that, and the energy medicine people would pick that up. So you would earn money, and that would benefit the university.
Sure. Thank you for the question and for the suggestion. Yes, our research group is always open for collaborations, whether in research or in industry and commercialization. I'm sure my supervisor will be quite excited to hear about potential partnerships. And with regards to your question, yes, we could expand the range. So, for example, how we make light emission color is combining three main colors of light, red, blue, and green, right? And with europium and terbium, we've only tried to tune it combining those two colors. In fact, in some of my other presentations, I have something called a CIE chromaticity diagram, which shows I can basically get CIE chromaticity diagram, where I can basically produce any color that I want just by mixing different amounts of red, blue, and green emissions, right? So some of the continued research that we're doing is adding a blue emitter into our frameworks so that we can control it and even towards white light as well as any other color in the visible spectrum. And with ultraviolet, we could also do that because some of our other lanthanide metals emit in the ultraviolet radiation. So we haven't looked on it really because there's so much things that we could look on, so we haven't really focused on that. But if it's towards, as I said in my introduction, specific targeted applications, then we can definitely go into that and look on it and use lanthanide metals which emit in the ultraviolet radiation. Sure, and this is my email, so you can always contact me anytime.
Thank you. Any other questions? No? Thank you, Mr.
Right,
Mayor.
thank you for your attention.
All right. So next, and suitably so, we're going to have a presentation on the fabrication of and electrochemical characterization of rare earth doped sensitized solar cells. And it's Mr. Leaford Henderson who is going to be doing that presentation.
Thank you. Much better, much better. So yes, I'll be presenting to you on fabrication and electrochemical characterization of rare earth doped dye-sensitized solar cells. All right? So, the outline of my presentation is very simple. I'm going to give you an idea of the background, the motivation behind the research, the methodology, or the steps that we took to find out what the answers to the questions we asked were, and then the results and discussion, and a brief summary. But first, if I was to think of a question that summarized the research that I'm doing, and I thought very hard about this, the best question I could come up is this. In mango season, would you eat mangoes or fast food? Think about it. Think about it. Here's the idea. Imagine you're living on an island, and we live on an island, with limited sources of food. You have mangoes, which are free, and you have Sandwich King, not the other company, but Sandwich King sandwiches. The mangoes are free, but you must pay a one-time cost for special mango collecting baskets. So you buy the baskets, and after that you can collect all the mangoes you want for free. The baskets are expensive, $100,000 each, but you only need to buy them once. However, if you choose the sandwiches, you must buy them daily for $500. Which would you choose? Which of these two options? All right? And then two subsidiary questions. One, is this a feasible situation? And two, what would you do to make the situation better? You could plant your own mango tree, but assuming that that's not an option, think about it. The idea here is if you have one resource that is quote-unquote free, it doesn't require daily investment, and you have another resource which could meet sort of the same needs, but requires continual investment, which one is better in the long run? So keep that in mind throughout the presentation. All right? So you have your mangoes, you have your Sandwich King sandwich, you choose the best option. For me, I'm hoping you'd guess the mangoes. All right? So the background. Conventionally, energy can be a very expensive commodity, especially in the Caribbean region. In the Caribbean region, you know, we lead the world in several areas. Unfortunately, one of those areas is with energy costs. And if you look at Jamaica, this is the average energy cost for our region. Jamaica, of course, being a world leader, unfortunately, has tended to have extremely high energy costs because we don't have oil. All right? Now, in addition to that, you have to remember that conventional methods of energy generation are less suitable than desired for several reasons. It's a dwindling resource. There are environmental effects. However, in contrast to that, solar is a potential solution, a potential source of mangoes, so to speak. All right? Because solar is available. It's an available resource. There's plenty of sunlight that reaches our surface. And if you look at this quote, it says more energy reaches the earth in 1 hour than all of the energy that we consume, and we consume a lot of energy, in an entire year. The cost tends to be high, that initial cost. So the mango collecting baskets are expensive, but you only need to buy them once. All right? So, mangoes or sandwiches? Now, typically, and this is actually a good graph, the price for solar material, silicon-based solar panels, has tended to drop over the last few decades. However, there was a peak, a small peak, which occurred between 2006 and 2009. And I always ask people to guess what they might think happened between those years. Can anyone guess? Anything significant? Well, the iPhone was actually released around this time. And remember that the iPhone and all consumer electronics use silicon. So if you have silicon for solar panels, silicon for consumer electronics, there's always going to be an issue of supply and demand. All right? So we are looking at dye-sensitized solar cells. They do not use silicon. They're a layered device, so you have these different layers here, and each layer serves one aspect of the energy capture, charge conversion, and current production process. Right? And so essentially you get a cycle, which is animated here, that behaves as a pump for electrons. Electrons are pumped out of the cell on one side, re-enter the cell on the other side. We are focusing on the white spheres that you'll see in the animation, these white spheres of titanium dioxide. And that's what we're going to pay attention to, and that's what we have paid attention to throughout this research project. So another question, why doping? And I wasn't supposed to put this slide here, but doping, the simple answer is doping makes things better, quote unquote. All right? Doping tends to increase the performance of something. So that's what we're talking about. There's no relation to track and field. All right? So doping, what we know about dye-sensitized solar cells is that electron transport in the dye-sensitized solar cell occurs through trap states, which are energy levels located in or close to the band gap of the material. So in the material structure, there are states that are referred to as trap states that electrons can travel between as they move throughout the cell. Now we know, and it has been shown, electron transport takes place through those trap states, and the location and position of the trap states can be modified by changing the properties of the material that we're dealing with. So by doping, by introducing external impurity elements, we can modify the behavior and modify the electrochemical characteristics of our cells by modifying the trap state density. All right? So an overview of the methodology is that whoa, that was fast. So we start with the metal iron precursor, which is titanium isopropoxide, and essentially add all the raw ingredients, so to speak, that are necessary to form these titanium dioxide nanoparticles with the right size and the right shape in an acidic medium. They undergo hydrolysis, and eventually at the end of this process, we get a white paste, which is heated at a high temperature and is formed into the cells. So we start with a clear liquid, and at the end of the process, we end up with these white spheres, white circles, which can then be soaked in the dye and converted into our solar cells. So the major aims of the research project were: 1, investigating the effect of dopants, lanthanum, praseodymium, and cerium, on key cell characteristics. As you heard from Mr. Min, lanthanides are very special. They have some special properties, and there's a reason why we chose these 3. In addition, we wanted to investigate the effect of monitoring or modifying the sintering process on cell performance. And the 2 things that we decided to change were sintering temperature and sintering time. This based on advice from Dr. Farhat, my supervisor. So the first thing we did was to investigate the effect of the dopants. So we had these 3 dopants. We investigated the performance of cells prepared with these 3 dopants at 4 dopant levels, in addition to undoped cells. And these were characterized under fake sunlight, standardized sunlight, just to make sure that we had a reference, a stable baseline. So for our first dopant, praseodymium, this is an IV curve. Basically, the higher up the curve meets the x-axis and y-axis, so this point right here and this point right here, is the better the cell is performing. And the further the curve is pushed towards the upper right is, again, the better the cell is performing. So for praseodymium and cerium doping, we essentially got lower performance. The cell current, the cell voltage, and overall efficiency dropped compared to the reference. This is for praseodymium, and this plot is for cerium. So our reference is up here, and our doped samples are down here. However, lanthanum doping tended to produce a slightly higher current density. So our reference is right here, and then these samples gave us more current, higher intercept on the y-axis, and the voltage was, again, relatively good. And looking at the performances that we got, 2 of our samples actually gave us a higher current compared to the undoped sample. This is for lanthanum doping. And 1 of them, a third, gave us a higher efficiency compared to our undoped sample. Now, existing literature does state that based on the dopant range that we chose, lanthanum elements will have different ranges for ideal performance. Cerium, in particular, tends to reduce efficiency above 1%. And we were doping between 0.25 and 5% throughout our dopant study. All right? Even when we went down to a dopant level of 2%, that's still relatively high. And that could explain the reduction in performance that we saw. So, after we investigated the effect of dopant addition, we took the best performing cell sample, which was lanthanum at 2%, and then investigated the effect of sintering temperature. So now what we did is we took this best performing cell sample and heated it at different temperatures. The heating is that final step before we begin to construct the cell. And we use temperatures ranging from 300 degrees to 600 degrees. And again, you can notice that this particular sample in blue is pushed up to the upper right, has a higher intercept here, larger intercept right here, and this corresponds to a sample that was sintered at 400 degrees Celsius. Compared to the other samples, the 400 degrees Celsius sample had a higher efficiency, higher cell voltage, and higher cell current. This essentially told us that the best sample temperature to use was 400 degrees Celsius. Another analytical technique we used was open circuit voltage decay. And for the two best performing samples, this peak, this characteristic peak from the open circuit voltage decay graph is shifted, and this is correlated to a shift in how the cell recombination is affecting the cell performance. This again tells us there's something special about these two particular cell temperatures that we use for sintering. Now, it's been noted in literature that as you heat titanium dioxide at higher temperatures, the crystal phase moves from a highly catalytic form to a less catalytic form. And the less catalytic this form is the less the push for electrons around the circuit is, which could again explain the reduction in performance that you see at higher sintering temperatures. Now, we carried out another analysis referred to as impedance spectroscopy. Essentially, we give the cell an AC signal, an AC current in black, and measure the current that comes out on the other side in red. And you apply one waveform, you get another waveform out. By analyzing these two waveforms, we can get a plot of the impedance in the cell, which is similar to cell resistance, and that gives us more information about how charge is transferred through the cell. The plots that we got for cells sintered between 300 degrees and 500 degrees look like this. And if you summarize this in a table, what these plots tell you is that the electron lifetime, plotted in this histogram, is greatest for cells that are sintered between 350 degrees and 400 degrees. Remember, we said that 400 gave us the best overall performance. Here, this is saying that electrons can travel through the cell for a longer period of time if it's sintered at 350. Again, slightly less than the best performing temperature we saw earlier, but still in the range. And this is telling us again that 350 degrees to 400 degrees is an ideal range for preparing our samples. All right? Now, the final thing we did was to investigate the effect of sintering time. So, remember, we took the best performing cell fabrication, the best performing cell paste with the best dopant at the best dopant level. We investigated that at the best temperature, and then now we took the combination of these two and investigated the sintering time. So we kept it at 400 degrees and measured how the efficiency changed at sintering times of 30 minutes, 60 minutes, and 240 minutes. And what we found is that the best performance was for the cell that was calcined or baked at 30 minutes. After that, the cell performance decreased. Now, the rationale behind that is that the longer you sinter this material, the longer you bake it. If you've ever baked a cake and you leave it in the oven too long, instead of being soft, it gets hard. And I can say this with, I know this from experience because I've done it myself. All right? Not intentionally, of course. The longer you sinter is the less porous the structure is. So instead of having something like a sponge, you end up with something like a cement brick. This less porous structure means that it can't absorb as much dye. And because it can't absorb as much dye, then you get less current being produced. All right? So in summary, we were able to use a low-cost aqueous method to prepare photoanodes for these cells. We investigated doping with rare earth elements to find the best dopant and best dopant level. And for the ranges that we examined, praseodymium and cerium produced a reduction in cell performance, while lanthanum doping at 2% in particular produced an increase in the overall efficiency. And that overall efficiency increase was by up to 25%. The optimum sintering temperature and time were 400 degrees Celsius and 30 minutes. And the overall increase in performance by optimization gave us a 39% increase in device efficiency. These are some publications that have been done on the project so far. Some acknowledgements: Department of Physics, Mona School of Engineering, Office of Graduate Studies, and the Shands Research Group at the University of Florida. And I thank you for your attention.
All right, thank you, Mr. Henderson. You should have told us or suggested what type of mango you were talking about. You know?
Well, I wasn't going to get into that argument this afternoon.
Any questions?
No? Yes? Yes? No? Yes. Well, the sintering, again, going back to baking a cake. You bake a cake at anywhere from 150 degrees, and don't hold me to this, I'm not a baker, but 150 degrees to 200 degrees, but you obviously don't eat it at that temperature. So you take it out of the oven and you make sure that it's in a safe environment and you let it cool naturally. A limitation of our study is that we really should have done this under an inert atmosphere, because the inclusion of any random stuff, so to speak, could have affected our study. But based on the limitations that we had, and based on what existing research groups do, we weren't able to carry that out. Yes, Dr. Stevenson.
If you took your material one test and then retest it again, do you see the same efficiencies you saw in the first one, or does it vary over time?
Thank you for that question. So I think it's actually, I'm forgetting if it's on the slide or in the appendix, but essentially the cells were prepared in batches, replicate batches. So we had triplicate cells, and each cell was tested 5 times, and then those 5 times were produced into a cell average. There is variability between each individual test, but what we see presented here are averages across the batch. So that helps to improve the repeatability of the results. That's true. That's true. That's true. That's true.
Following on from that question, yes. With the slide with the doping with lanthanum,
yes,
you had said that there were increases. Right, but the increases that you observed were in the 50 and the 100, right? So,
all right. So
is the sample lanthanum 025? Does that have to do with any the numbers? Does it have to do with any concentration?
So lanthanum, well, it's actually on the slide. Lanthanum 0.25% molar percentage relative to titanium. That's this one.
So my question is 1%. It's not a trend. It doesn't correlate, because you see the 6.88 in the 25, but not in the 5. But you see it in the 100, but not in the 200. So my question is, following on that, is there a reason that those particular densities are, you see that those
values?
Is it a random distribution?
That's a good question, and I thank you for it. It's actually a very good question. So in general, the trend that we see is that at higher dopant concentrations, the cell current decreases because the electrons end up being trapped. The additional trap states help up to a certain point. And you notice that in general, even though it's a very slight trend, the electron current is decreasing at higher dopant levels. However, the actual answer to your question is that even though we know that this trend exists, we don't have a model to explain it yet. And there are a number of factors, so we don't know exactly how the ions are being included into the crystal structure. So it could be we have cases where the dopants are on the surface of the material, where we have surface states being induced on our titanium dioxide. It could be that for one of these, the dopants are inserted deeper into the crystal structure. There could be modifications to the crystal structure as well, and we really don't know at this point. So that would definitely fall under future work to clarify what's happening.
Do you have any idea to how you want to, monitor or control, monitor that?
Okay, so for monitoring the crystal structure, we could use XRD. I think XRD would be one of the best ways to identify what's happening. And XRD could also give us an idea of the band gap, which would allow us to potentially model directly the effect of dopant concentration on the other electrochemical properties that I suggested earlier. So that's one that we've looked at. There was work on using Raman spectroscopy, but I have never done Raman before. But I've heard it mentioned before.
All right, thank you. One last question.
Yes.
Very interesting presentation, Mr.
Thank
Anderson. I presume that this is with a view to building a good mango basket. To use your analogy.
Yes.
Because we already have silicon-based mango baskets. So can you tell me how this would translate into being more effective than purchasing an imported mango basket?
All right. Well, I think the answer to your question has two parts. One is that you have to remember that these cells that we produced were produced here in Jamaica. So the titanium dioxide, although we have to import the raw chemicals and the ingredients and reagents, the assembly takes place here. And because you're not using the high temperatures that silicon takes to purify it, a dye-sensitized solar cell manufacturing plant could theoretically be constructed in a location that doesn't have access to cheap energy like all of the silicon-based plants are. Because around the world, I think it's only 5 large plants that produce silicon. And even though we have tens of solar cell manufacturers, they really only get it from 5 main suppliers. So that's half of your question. However, the dye-sensitized solar cell itself is one of several hybrid organic solar cells that are under development. The perovskite solar cell in particular is actually much better than the dye-sensitized cell because, for one, the dye-sensitized cell has a liquid electrolyte. But if you have a solar panel on your house and your house temperature drops or climbs, liquids expand, liquids can freeze, liquids can find their way through cracks and crevices. So this particular type of cell that has been invented recently within the last decade or two is actually, it builds on this, but it takes it to higher levels. So this is really just an idea of the kind of research that could be done in taking perovskite cells or other developing technology to a new level as well.
Okay, thank you very much. Okay, so next up, we're going to have Mr. Jermaine Smith, who's going to continue talking about rare earth metals, and he's going to talk about the rare earth coordination polymers from ditopic carboxylate linkers, potential for sensing and gas storage. Let's give him a moment to get set up here.
I don't know how to use it. It's okay. Oh, I can't just put it here. Hello. Good evening, everybody. Are you hearing me properly? Okay. All right, I'll use this one. Thank you. All right, so it's a pleasure to be here. I am Jermaine Smith, and I'm a PhD student in the Department of Chemistry. Today, I will be, today my work is, or my presentation, I won't spend so much time on introducing the SBUs, because I'm honored, or I have the pleasure to have my research partners there, go before me. Right, so some things I won't go in depth into, but I'll try to, relate to you my research, especially on the potential applications of these metal organic frameworks for sensing and gas storage. So we have the new rare earth coordination polymers and MOFs using ditopic carboxylate linkers. What are coordination polymers? According to IUPAC, a coordination polymer is a compound in which metal ions or metal ion clusters are bridged by organic linkers, forming 1, 2, or 3-dimensional extended frameworks. So here we have the crystal structure of a 1-dimensional and a 2-dimensional coordination polymer. Research into coordination polymers has attracted much interest in recent times due to the tunable nature of these materials, as there are a wide range of metal ions and organic ligands that could be used to make these frameworks. A special class of coordination polymers that has attracted much interest in recent times are called metal organic frameworks. So these are coordination polymers with a well-defined framework topology that are often porous. All right, so we can imagine how an inorganic building unit, which would serve as the node, would combine with an organic building unit to form this three-dimensional structure with the potential to have pores. In fact, metal organic frameworks are some of the materials with the most high surface areas, having surface areas far exceeding traditional porous materials such as zeolites and activated carbons. So there is much interest, or there is much gain in finding or being able to make targeted materials, right, to control the geometry and the structural characteristics of these materials to use them in particular applications. One of the main concepts that have been developed in coordination polymer chemistry is that of the secondary building unit concept, which was developed by researchers such as Yagi and O'Keefe. And they identified this robust and repeatable unit called the secondary building unit. And by identifying the conditions under which these SBUs form, it is possible to form frameworks with similar topologies, overall topologies, but tuned chemical and physical properties. Hence, so these systems from A to C are called an isoreticular family. So in forming an isoreticular family, it is possible for you to make targeted materials. And one of the main things is to identify the SBUs. So there have been several SBUs that have been identified since the development of reticular chemistry. So you have finite, one-dimensional, and ZR took you guys through the two-dimensional or the tertiary building units. All right. So there is much gain in controlling, right, identifying the conditions under which you form a particular SBU, and then using those SBUs and changing the organic linker to form a particular type of framework. In fact, many transition metal systems have been exploited for particular applications in gas storage and separation, drug storage and delivery, catalysis, magnetism, medical imaging, and for sensing applications. For my presentation today, I would focus on mostly sensing applications of these materials. For example, due to the porous nature, what you are trying to do, if there is a particular signal or a unique signal obtained from the framework upon interacting with a particular analyte, then we can use those systems as sensors for that particular analyte. So most of our systems are made with transition metal ions, however, due to the predictable coordination behavior, which makes the rational design and synthesis for specific applications easier. But there are significant advantages to be gained by incorporating rare earth metals into as nodes in coordination polymers. So we are familiar with the rare earth elements, so they comprise the lanthanides as well as scandium and yttrium. And we know in Jamaica, we know about the rare earths because we know that they are in the red mud from bauxite. Right? And recently there was a pilot project between the Jamaican government and a Japanese company called Nippon for them to extract rare earth oxides from the red mud of bauxite. So these are the lanthanides, right? And in the presentation, I may use rare earth or lanthanides just because, you know, sometimes we use them interchangeably. I must also mention something called the lanthanide contraction, and this has significant effects on the formation or the types of structures that are formed during my study. So essentially, it is a decrease in the size of the lanthanide ion as you go across the series. But that is not uncommon. It is not unique. But for the lanthanides, it leads to steady and subtle changes in properties of the materials that are not commonly observed in other groups of elements. So the lanthanides have, or the rare earth elements have significant, you know, optoelectronic, magnetic, and catalytic properties. So they are used to make some of the most powerful magnets in the world. So magnets that are used in your cell phones, in MRI imaging. For MRI imaging especially, we also have gadolinium compounds that are the most widely used NMR contrast enhancement agents. Due to their optoelectronic properties, lanthanides, or the rare earths, are used as phosphors in television screens, and television and computer screens, as well as security features in euro banknotes. So there is significant advantage to incorporating the rare earth elements as the nodes in these metal organic frameworks, but there are challenges, however. So due to a spherical crystal field, the coordination behavior of the rare earth elements is less predictable. In fact, while there are many isoarticular families of transition metal compounds, as you can see from the Zayar's presentation, we were one of the first groups to form an isoarticular rare earth family of compounds. So you have many transition metal reticular families, but only, I think, currently have only 4 of those families for the rare earth elements. Hence, we need to, so the studies are limited, but in order for us to take full advantage of the properties of these materials and to be able to make targeted materials with specific properties and applications, we need to make many more rare earth coordination polymers and MOFs to characterize them and look at the topology so that we can extract trends that can lead to a rational design approach toward specific applications. In light of this, the aim of our study is to make novel rare earth metal coordination polymers, study their formation and structures in order to identify the trends that can lead to a rational design approach, and also to assess the potential of these materials for applications. Our design strategy is to use ditopic organic ligands. So these are the ligands that we use. So they are different forms of terephthalic acid that have different functionalities connected to them. And so first we seek to use similar ligands, right, where the functional groups are different. And we would hope to, as Zara spoke about, initially, we sought to do some form of serendipitous synthesis. But, it is only in doing these kind of syntheses and making more compounds that we can then, kind of do a sort of a retro-synthetic analysis to identify the conditions that would lead to the formation of particular frameworks. When we analyzed the Cambridge structural database, we found that these ligands either had limited or no structures with rare earth elements. Also, the carboxylates bind very strongly to the lanthanide or the rare earth elements. Hence, you have a tendency to form stable frameworks. Also, these pi systems or systems with conjugated pi systems are good harvesters of light energy, which can then be transferred to the metal centers that we can use them for, or we can exploit their photophysical properties. Our methodology involves mixing the ligand with the rare earth salt and exposing it to hydrothermal conditions in a Teflon-lined autoclave, which is then placed in an oven at approximately 180 degrees C, or exposing it to slow evaporation conditions in conical flasks. The characterization methods include single crystal X-ray diffraction, which allows us to see the connectivity of the components, metal ions and the ligands in our structure, as well as powder X-ray diffraction, elemental analysis, FTIR, and TGA DSC analyses. When we use the NTA ligand, which is 2-nitroterephthalic acid, we obtain 9 compounds with 4 different structural types, you can see here. And we use varying conditions, either hydrothermal or slow evaporation, and we could see an effect of the lanthanide contraction as well as reaction conditions on the formation of our structures. Here we have some beautiful microscopic images of single crystals obtained during or as we form the compounds. With the NTA ligand, we form these structures As you can see, the structures are beautiful, aesthetically pleasing, and also, so they are aesthetically pleasing, right? They were formed with these rare earth elements. But, ladies and gentlemen, for the sake of time, I just want to focus a little bit on UEMOF 11. UEMOF 11 is a three-dimensional structure that has water molecules in the pores. Not only that, the nitro group is exposed to the internal surface of the pore. What we have done is to remove those water molecules and the structure remains stable, right? So now we are looking to assess the ability of this system to be used as a gas adsorbent. And based on studies done by researchers such as Paniarat and Matey, they have found that when the nitro group is exposed to the internal surface of the pore, that increases the carbon dioxide adsorptive property of the material. This work was recently published and well received in the scientific community, has seen by 5 citations already garnered. With a TFTA ligand, we obtain, and the lanthanide and the rare earth chloride, we obtain 2 series of compounds. Sorry. 2 series of compounds, UEMOF 12 and 13. UEMOF 12 and 13 are 2-dimensional structures. And let me focus a little bit on UEMOF 13. It's a 2-dimensional structure that features fluorine to fluorine halogen interactions. These interactions, while common in organic systems, are uncommon in coordination polymers. So this gives us an opportunity to assess the role of these interactions on the formation of these structures. Also, for UEMOF 13, the TFTA ligand serves as an efficient sensitizer of europium and terbium emission. That means when we shoot UV light onto these systems, we get a strong red emission for the europium system, as well as a strong green emission from the terbium system. Everybody would know who I made this one for. All right, this was made for my wife. Right, so what we did, due to the strong photoluminescent properties, what we did was to seek to use this as a photoluminescent sensor for metal ions, as well as for nitroaromatic compounds that are used as explosives in bombs. So what we did was to form a suspension of the compound in methanol in this case, and then we added certain amounts of metal ions as well as the nitroaromatics, and look at the change in the luminescence intensity. We found that this system could be used as a promising sensor for aluminum, iron 3+, and copper 2+. As you can see, based on the quenching efficiency, it is very high for these 3 metal ions as compared to the other metal ions. It can also be used as a broad-based sensor for nitroaromatic compounds, as seen by the high quenching efficiencies here. With the tetrabromoterephthalic acid ligand, we formed UEMOF 14 as well as UEMOF 15. The TBRTA ligand as well is an efficient sensitizer of europium and terbium emission. Hence, we went to look at the sensing abilities. We found that it could be used as an efficient sensor for iron 3+ and copper 2+, right, based on the strong quenching efficiencies. And when we looked for on the nitroaromatic compounds, it is a strong quencher. Finally, ladies and gentlemen, I'm out of time, but I must draw your attention to UEMOF 15, right? This system is a 3-dimensional coordination polymer that features or that traps rare earth octahydrate clusters. These clusters are surrounded by 12 hydrogen-bonded water molecules to form a 3D Star of David cage. Right, so water clusters are important because, especially when they are trapped in these systems, because they allow us to study the behavior of bulk water. Right, so we'll be looking at those studies in the future for this compound. In summary, we have made 39 novel structures. The compounds are promising for nitroaromatic and metal ion sensing, and this study brings us closer to the rational design of these materials for specific applications. In further work, we will seek to still form an isoarticular family of compounds, look at gas absorption and magnetic studies, and also to assess the recyclability of the compounds in sensing applications. These are my acknowledgements. I would like to thank these persons and entities for supporting me throughout the period of my studies. Thank you. Any questions?
Thank you. Any questions?
Driving here, I was listening to a radio interview that was emphasizing the importance of protecting the copyright. How do you go about patenting these new substances, and are they patented?
All right, so
are they automatically patented by virtue of you developing them, or do you have to patent them?
No, in our research area, forming the materials by themselves, we don't need to patent them. If it is that we find a novel application, for example, using these as sensors for copper 2+ and iron 3+, then we would seek to start the patenting process. But the first thing that we would do is to ensure that having formed the structures, we seek to publish them. Because in publishing the structures, we own the structures, and any patents generated from them would, would have to, so we would have to get some of those remittances.
Thank you. More.
Publishing the structure does not necessarily give you a patented right on the invention, right?
Well, so if you look on it that way, like so especially in our, this is a burgeoning field, right, where everyday structures are being published. So they would have to at least acknowledge that we are the ones who formed the structure, and then based on that,
you'll be cited in the patent that they file on your structure.
Go again?
You'll be cited in the patent that they file on your structure.
Well, yeah.
But you won't be able to claim, because especially if you haven't claimed any specific utility for this material,
right,
and somebody else uses that material for something else, I can patent it for this function.
Well, that is true. That is true.
Also,
can
by
patent it for that.
presenting your materials at a conference, presenting your materials on in a publication format without your audience agreeing to any kind of confidentiality, you've actually now, what's what I'm looking for, you've disclosed your invention, so therefore you've actually lose some grounds into your being able to protect it. So if you want to protect your research, things you have to think about before you actually tell the world about it is you have to do either, you don't have to be a patent, but you have to have like an invention disclosure, which is like a very simple thing. Basically, you can file, or you can do a poor man's patent where you put it in an envelope and you mail it to yourself, right? But there's lots of ways to get around. Publishing itself by itself does not protect you. Yeah,
I agree with that, Dr. Stevens. So I should have stressed that. Right. So, but if it is that you say that you especially in the publication, if you say that it is possible to use this as a sensor for that, and you go and you start the process. Similar to what you said, where you do the layman's patenting,
if you start it,
then you could do that. Right.
But if you don't, because one thing that people have done is gone back to old papers, taken their work, and then file a claim on it.
Yeah.
Going back to your sensing studies, though, so you had one slide, we had copper 2+ and iron 3+. Could you comment on the ionic radii of your cations that you're sensing? Is there similarities between them? And two, what's your limit of detection of iron 3+? And how does that compare to some of the best iron sensors we have out there, or even copper? Either one of them will do.
We didn't look at the limit of detection, but what we did look at was the Stern-Volmer plots, or the Stern-Volmer constant, right? So when you compare the Stern-Volmer constant to what they have in the literature, or systems that they are using in the literature, they are comparable, and in some cases it is higher. So I think for iron and copper, one paper which has the highest Stern-Volmer constant, it's like 10,000, I think, but in our case we have it at 5,000 something. But in general, the papers that show sensing for iron and copper would have the Stern-Volmer constant in the region of 5,000, 3,000, thereabouts. So it is comparable. What was the first question again? Okay, yeah. All right, so the ionic radii, I don't remember right now, but if you look at the charge densities, right, iron 3 plus definitely would be higher, and copper is similar for the charge density as it relates to copper 2 plus. Right, so the quenching mechanism, what you find mostly, especially when we survey the literature, is that sometimes there is an electron transfer process where instead of that energy reaching the ligand to be transferred to the metal, to the rare earth center, it is actually transferred to the metal center, such as the copper 2 or the iron 3 plus. So further studies will seek to actually look at the mechanism of quenching for our systems, and then we can, because it is important to know the mechanism by which the quenching occurs. Yeah, man.
Thanks. One last question.
Part of my field is the water business. I'm a registered water consultant, British expertise.
Okay.
So I'm interested in the water, because you mentioned water becomes sequestered in those cells.
In the cages.
In the cages. What I want to know is, what quality of water do you use? Because water could be monomeric, dimeric, polymeric. In fact, much of the water that we drink from the taps, it's lumbering. It's about 39 units, and which is really heavy water, which is not really good for the body. So I wonder, in your systems, which water is best for your, research? Is it the the dimers, the trimers, or do you deal with the heavy water in that?
Oh no, man. So in my systems, I make my compounds in water, but we use distilled water. So we do not use tap water. I do not use ultra pure. Oh.
You ever look at that aspect, or is that not relevant to your?
Yeah, we don't look at that aspect for my work. But as I said before, especially with UMR 15, we'll be looking to see if we can do studies that will allow us to assess, try and assess the behavior of water in these systems, so that they can form models that can model behavior of bulk water in different or varying systems. Yeah.
All right. Thank you very much, Mr. Smith. Let's give him a round of applause.
Thank you.
And we are going to move into our final presentation of this session. And it's going to be something a little closer to my field, improving the skid resistance and reflectance of road surface using crushed recycled glass. It's going to be presented by Ms. Candice Brown. Just give her a moment to set up, and some applause. That's good too.
Oh, you just. Good afternoon, everyone. Can everyone hear me? All right. So some of you might be wondering why I have this random number on the screen. I wish I could tell you it's the amount of money in my bank account, but unfortunately that's far from reality. However, the reality is that the first number represents the amount of persons who are killed in car accidents each year worldwide, while the second number is an additional amount of persons who are injured in car accidents each year. So 1.2 million persons are dying every year all over the world, while 50 million extra are being injured. Why do we have so many accidents occurring? What is causing this large number of fatalities? Well, a few reasons include but are not limited to error in judgments, excessive speed, disobeying stop signs and traffic lights, skidding, road not being maintained, and driving under the influence. Unfortunately, you can see here that most of it is due to human error. Unfortunately, I don't think I would be able to properly fix that issue, but what I think I can do is fix the issue of the road surface, in particular, skidding. I'm not the only person, however, who have seen that this is an issue. Persons have been doing this for years to try and investigate what is it that is causing this and how can it be improved. A research was done in 2009 where they tested how skid resistance affects traffic safety under wet pavement condition. They were able to conclude that the water on the surface does in fact affect the resistance. Someone else has done research in 2007 where they adjusted the asphalt content to see if this affected the resistance. And what I took a particular interest in was the use of solid waste materials in asphalt mixtures to see how they affected the characteristics of the surface. So that brings me to my topic, which is a study on the use of waste glass to improve skid resistance and reflectance under wet pavement conditions. My name is Candice Brown, and my supervisor is Dr. Victor Dose. You see me using this term skid resistance throughout so far. So what is it? What is skid resistance? Well, skid resistance is a measure of the frictional characteristics of a surface. That is to say, it is the force that is developed when a tire that is prevented from rotating slides along the pavement surface. So let's say, for example, you're driving down the road and something just jumps out in the middle of it. You have to make a sudden stop, so you slam down on your brakes and your tires stop rotating. Now, what prevents your car from moving a distance beyond that point at which you stopped is skid resistance. So if you slam down on your brakes, your tires stop rotating, and you still move a distance, you have skidded. So I'm trying to reduce that distance at which you travel, which would in turn reduce the amount of accidents that occur. So what affects skid resistance? Ideally, in a heavenly world, you'd want something that's resistant to weather, something that's non-polishable, and a surface that is resistant to moisture and texture. However, in our reality, or the road to hell, it's affected by things such as surface texture, the climate, the temperature, presence of foreign materials, and moisture. So my research will be focusing on, oh, no. There we go, right. So focusing on surface texture. How will I do it? So my plan is to use recycled crushed glass to add texture to the road surface of areas more prone to skidding, which should improve the overall friction and resistance. I emphasize more prone to skidding because not everywhere along the road surface has this issue. Areas such as inclines or curved inclines where you're going down a hill or on a corner, those are areas more prone to skidding. So I'd want to apply the glass to those sections to reduce the amount of accidents that occur. So what's my methodology? What I'm doing is that I'm sieving crushed glass into different size fractions. So far I've used two, 1.18 millimeters to 0.6 and 0.6 to 0.3. Once sieved, I apply it to the surface of a pure sample with epoxy, and I use a British pendulum to test the skid resistance of the surface. Once I have those values, I compare the pure to the altered samples, right? So what have I, well, this actually focuses mainly on skid resistance, but you can see from my title that I'm also looking on the aspect of reflectance. Now, there are two things that come with the issue of reflectance. One, whenever you're driving along the road and the surface is wet, if there is, when the lights are incident on the water surface, not everything is reflected back to you. Some of it is lost. This is an approximation, by the way. Some of it is lost to reflectance, so the amount of light that you see is reduced. In addition to that, ideally, you want the surface to be rough so that the light isn't all coming back to you in a concentrated beam. When the surface is rough, it's being reflected at different angles, so you're able to see generally and not everything being shown right back into your eyes, all right? But when you have the layer of water on the surface, it's smooth. So it creates a barrier between the surface of the road and the light itself, so that everything is coming back to you. I'm not sure if a lot of you, well, you should. If you drive at night when it's raining and the light hits the surface, you're seeing a concentrated beam of light. and that affects your ability to drive and see clearly. So with the addition of glass, I want to have that extra layer so that the water isn't creating that smooth effect, and it's also, when you have that barrier, it will reduce the layer of water that you're having on the surface, so you're not having as much loss to refraction. It's an area that I would like to explore. However, the methodology hasn't been completely refined, so I don't have any results for that area just yet. So what do I have? To make my samples, I actually have a few here that you can view. I'll pass it around, but they're still being used. So you can view at the end if you so desire. Right. So to make a sample, I am required to heat asphalt and the stones. So these stones are actually different size fractions, and it's a mixture of crushed gravel, sand, and filler. I mix it with a certain asphalt content and ensure that it is mixed to maximum distribution. Once I have achieved that, I place it in this mold and ensure that all the corners are filled so I can get a uniform shape. Once that is done, I have to compress it using a drop hammer, which is very heavy. Built some muscles while doing this research. So I compact it, and this is the end result for my samples. Once I have that, I use epoxy and apply it to the surface to get a sample looking like this. Now, to test the skid resistance of the surface, I use a British pendulum. Now, what happens is that you have this pendulum attached with a rubber bit at the end, which swings and brushes the surface of the sample and reads off a number along here that will tell me how much friction this surface has. So what I've received so far based on my preliminary tests was that I got a number of 61 for a dry, pure sample, and a number of 31 for wet. Now, the reason I have to do this under both dry and wet conditions is that skid resistance is affected by moisture. Whenever you're having that issue of skidding, it's normally when the surface is wet rather than dry. So I'm seeing how much does that number vary versus wet versus dry. So I saw that the number is significantly reduced. However, for the crushed glass, well, one with 0.3 to 0.6 millimeters, you see that the number did in fact drop when wet. However, it's still greater than that of the pure sample. And of course, the bigger size fraction had a greater value as well. So from this, I was able to conclude that yes, skid resistance does in fact decrease when the surface is wet, and when you add crushed glass to the surface using epoxy, it does improve the skid resistance of that surface. Now, I specify epoxy because I'm also exploring other methods. Instead of using epoxy, I am looking into the option of tamping it, where I'd apply force to the surface of the glass while it's hot, of the asphalt sample while it's hot, so that would eliminate the need for epoxy. So that is also being explored, and I'm also exploring using different size fractions of glass to see what size would be more optimal for this study. Right? That brings me to the end of my conclusion, my research, sorry. Thank you for your attention.
Okay, thank you very much. Any question?
Thank you, nice talk. Well, quick question for you. So I live with someone who does construction. I always hear an engineer's job is to reduce cost. So when you're now going to apply epoxy and then do your crushed glass, how does that now change the cost of building a road? And two, you're looking at the road, but how can like tire technology be changed, which in my mind might be a little bit cheaper and less invasive to make something that's more skid resistant? There's two questions. One is, what would the cost be like to implement your technology right now to put the epoxy on your glass compared to how much you spend now, because cost is going to be important. And two is, you're looking at the road, but isn't tire basically making better type of tires, like snow tires or something else, might be another way of fixing this that will lower costs?
Well, all right, to answer the first question in terms of cost, I'm not entirely sure what the cost of bulk epoxy is at the moment. However, I do know that for one sample, a tube of epoxy costs like around $800 or $800 to $1,000 to make one, right? So I know it's pretty costly. That's why I'm also looking into the aspect of tamping, so that I would not have to use epoxy at all. So this is just one aspect that I've currently explored, and I'll soon explore another to eliminate that completely. As for the tire aspect, it is something I am interested in looking into, but then I'd have to consider the fact that if I implement these tires, will people want to buy it? Because they know that they have these tires and the tires are fine. Will they want to spend the money to get these additional set of tires? I'm not sure. But currently, I'm looking at aspects of the road surface. What can we do to fix our roads versus what can people do to change their cars? I'm not sure if that answered your question. Okay. Right. Epoxy itself does apply a smooth layer, but the glass would be embedded completely into it. So that even though you're having that additional smooth layer, the glass is on top of that to add to the friction itself.
And I have a question. It's generally for asphalt roads or bituminous roads that you're talking, that this application is for, but there are also concrete roads as well.
Right. Yes, I'm mainly looking at concrete roads, but considering the application, it should be able to be used on other road surfaces as well. Because if I'm using epoxy, epoxy can go on almost any surface as far as I know. So with the addition of the glass on those concrete roads, it should still be able to increase the resistance. If I were to do the tamping method, not entirely sure about that one just yet.
You probably want to compare some of your results to a datum of a regular bituminous road and a regular concrete road.
Thank you for the suggestion.
Earlier, I'd mentioned about the use of plastic, and I'd like to add rubber, you know, because there's so many rubber tires, and they collect water and mosquitoes, and kids get poisoned and so on. Have you thought about using that? Because you mentioned in your research that you're looking at the moisture film on the road surface, and as a driver in the past, I've experienced aquaplaning. So a lot of drivers have come down with that, and then when you brake, you know, you still go into whatever it is, and a lot of people have paid out money in big accident bills. So I thought that the use of the rubber and the plastic, wouldn't that help you better towards attaining your goals in terms of the moisture film? And also it might work out cheaper. Glass, I'm wondering about. Seriously, and what about microabrasion of tires? Is there any possibility of that with the glass?
Well, to answer the first part about using rubber and plastic, it was something considered. However, I'm trying to use something that will not wear down too quickly over time. If I were to use plastic, it has that issue of polishing, where the more something rubs against the surface, it will become smoother over time. So that would happen quicker than it would for glass. No, in terms of, what was the second part? The same thing for the rubber and the plastic. It would be polished a lot quicker than it would for glass because glass is more durable. But you had asked another question. Can you repeat it? Oh, in terms of how it affects the tires? All right. If I were to use the glass on the surface, it wouldn't be a situation where it's being added along the entire surface, where it's a constant friction being added to the surface, that the tire is being rubbed over it over and over and over. It's just for certain areas that are more prone to the skidding, so that when you make the sudden brakes there, you wouldn't be sliding too far down. So it's not an issue if it's just at those sections along the road. So it's not a constant abrasion being added to the tires, just for certain areas of the road. So it wouldn't be as much of an issue.
Okay, thank you. Any more questions? All right, thank you very much. Let's give her a round of applause. She has some samples here if anybody would like to take a look. And that brings us to the close of our parallel session here on energy and materials. And we are scheduled for a break before we move on to the legacy talk, which begins at 6 o'clock based on the schedule I'm looking at. All right.
Okay, good evening, ladies and gentlemen. Welcome to the final session of day 1 of the FST conference. This is entitled The Legacy Talk, the title of which is The Development of the Science Faculty at UCWI. Our speaker is Emeritus Professor Robert Lancashire, who, when he retired in 2015, was Professor of Computational Chemistry here at Mona. He is originally from Australia and joined us at Mona in 1979, and he's held positions of Sub-Dean for Technology and Deputy Dean in this faculty. Well, he's a computational chemist who spent a lot of his working life applying modern computer methods to assist in the delivery of chemical information. I won't read the entire bio, but he is the author of the code behind a little program called Chime, which went on to do big things, and he has been involved quite a bit in the UPAC, the International Union of Pure and Applied Chemistry. Okay, we're going to hear about, I think, the physical space that we occupy in the faculty and how it's changed or not changed through the years. And to some extent, the people and personalities that shaped the development of the departments and the faculty. Professor Lancashire is a keen amateur historian, and he's also, I'm coming to that. He is the co-author of a book on the history of the Department of Chemistry, so you know that indicates how strong his interest in this aspect of things is. He is an intrepid photographer. You know, I won't tell any tales. So we can expect a very visual presentation, lots of pictures, not that he would have taken them himself, but he is very keen on the visual images. So I won't speechify anymore. I'll turn over the proceedings to Professor Lancashire, who will speak for about 40 minutes. Whereafter,
I can then get 10 minutes just to show pictures.
Whereafter we'll open the floor for questions, comments, and discussion.
Okay. As Prof. Jacobs mentioned, I've been here for nearly 40 years, and so the disclaimer is that if you're worried that this is going to be very chemistry-centric, I have tried hard to diversify it a little bit, but 40 years in chemistry department means that there's clearly going to be a lot based around chemistry. The other thing was that by and large, the people that I've selected to try and write something about are all dead. And the reason for that is that nobody can come back and say, damn so-and-so, you didn't do me justice, you gave him 1 page and you only gave me half a page, and so on. So with a few exceptions, most of the people have already passed on. And to try and guarantee that, I decided that it would be best if I stuck to UCWI days rather than UE, but I have had to come up a little bit. All right, so you can see that clearly there's no way I can do that in 40 minutes. All right. These were the slides that I've got, and it's all up online. If I come back. There at the bottom, it's up online, so if you want to get a copy, you can pull along and read it on your phone now, since we have Wi-Fi in here. All right, so the ones with red are former deans, and so I'll try and at least get to them. There are a few others that were heads of department and but let me start straight off. The first principal, of course, was a chemist, so they knew what they were doing when they started, right? And he lived just a few doors up from me now, which looks a bit like this, but going back a few years, it clearly didn't have this extra section and the veranda around the front of it. So this was 62 Lady Musgrave. And Taylor was brought in and realized that if they could get hold of the Gibraltar campsite, there already were huts there, and so they had some buildings that they could start and get people into and get things moving while they then tried to build. So his was the groundbreaking for Gibraltar Camp. Then you can see the start of the building of some of the huts a little bit further on, and then eventually there was 100 and something or other huts that were here on the campus. There's hardly any of them left now, as you'll see. Across the road, the Mona Dam started about 46. He was one of the buildings. This one was called the Nunnery, and the group here were in fact waiting for the installation of Princess Alice back in 1950. Amongst them were a couple of science people, plus a few from ISA, and Elsa Gavaya is the one on the bottom right. So, in terms of staff, the ads went out in 1947. The Gleaner has been far more used than any of the records on campus in trying to find information. So you'll see a lot of bits that have been clipped from the Gleaner. Anyway, the first salary for a professor was 1,000 quid. And so things have changed a little bit. Not much, but a little bit. It was clearly a put-up job because, as you see, they advertised for a professor of chemistry, professor of botany, professor of zoology, but for physics we only want a senior lecturer. Couldn't afford the professor, right? And in January then 48, they announced who had been given these positions, and a few weeks later on, a number of them came out then to visit. So here's a very young 28, 29-year-old Hassel, and Asprey and Millett and Tommy Taylor was there as well. So at this stage, you'll see that it's Professor Asprey, Professor Millett, Mr. Hassel. He still hadn't done his PhD viva at that stage. Right? That was to come before he eventually got here in the September. This is a beautiful old photo from Owen Minot, one of the first med students. This one I think I may have taken in the early days, and these were certainly mine, which was the shameful destruction of the first lecture theatre and the original buildings. In terms of academic staff, in the very early days, the heads are there in red, and then if we come across a couple of years later, you can see that the numbers have grown a little bit to take into account that student numbers have grown as well. So, chemistry, Hassel, Martin, A.C. Ellington, who resigned within the year and was replaced by Lipman, and even from day one, we had a research assistant to help with some work in the labs, research labs. Ken Magnus was one of the first science students, and I got these letters from him. This one showing that candidates who were going to be hoping to be admitted had to do an examination, and then a month or so later he got this nice letter saying, we're welcoming you, you've now been successful in gaining an admission. So first year, 33 students that were all in med, so Hassel gave the very first lecture to med students, Then in the second year, we now have med and science, and the numbers, as you can see, doubled and doubled until we've now got arts numbers coming in as well. The Gibraltar labs, there's some big pendulums dangling here for a physics lab, some apparatus that the students don't have now, sitting in front of them in the labs, and another chemistry lab. Hassel is there in the back somewhere. These are some of the first graduates, and I've listed the first 4 or 5 years here. They had an arrangement that unless you were resident for a certain number of years, you were not able to graduate. And so you'll see here that people like Willie Chan and Donald Vickers, for example, had finished their exams in '52, but they had to wait a year before they could go through the graduation ceremony because they hadn't been resident long enough. In fact, Willie came in at the end of first year and joined in with the first group, did the exams with the first group and passed, but then had to wait and sit for a year while he was waiting. But of course, he started his master's even without his degree. Right? So it didn't stop him, it just, they all knew that he was going to come through because he'd passed all the exams, but he didn't have the qualification. There is a little table down here which I also found interesting. You'll note men, few women, men, few women. Think of your classes today and look at the difference. Yeah. So what we see here as well was for the first 10 years or so, 157 men, 37 women, 19%, 81%. So, you know, 80-20, right? It took 10 years for the first female student to get a first class honor. Right? So there were no firsts until that 10th year. There's all sorts of bias that we don't talk about. Anyway, resources. This looks like the engineering faculty, doesn't it? Isn't that equipment what's making up engineering? Right. It's the workshop, right. So here's glassblower, obviously got set up there as well. A little bit later on, these buildings started to come up, and these were just about done when Charlie came through in '51 and took off some of the roof off here. And you could see bright daylight through some of the early pictures of this building. The tree is still there as you walk down the car park, right? On the other side, coming back up, is the back of physics and what used to be electronics unit and whatever there, and the chemistry department office is up here. Aqueduct is there, horse is not there, right? Chapel's not there, right? That didn't come till later. There's no water in the dam yet either, all right? Although the space is marked off. And we're about here somewhere, right? The old science lecture theatre there, the faculty office would be here somewhere. So life science is now down there. Okay, the first postgrad, Vickers I'd mentioned as one of these students who had this residency problem and couldn't graduate in '52, had to wait back a year. He's the first that I found from the faculty coming through with a postgrad with a master's. Roger Cade was his supervisor, and Willie Chan was the first from chemistry. And you can see that the one that stuck out for me was this guy, Danny Campbell. And there's two articles in the Gleaner that talk about. His first one is here, which gives the title of the thesis for '55. And then there's another mention of him in '60-61 saying that he did 2 MScs with no title. I haven't found a thesis at London. And of course, in those days, invariably there were no records in our library because they were all taken up to London, and we didn't get copies unless the student had made extra copy for the library here. This was taken, I think, for around about the 50th anniversary. I managed to grab Cedric and say, look, come let me take a picture. So here's the old building, and this was a sign that used to be there, just going down to the senior common room, saying, you know, I gave the first lecture. So I find that as iconic. Anyway, this was taken at the 60th, a little sad in that Bunny's in hospital, having fractured his hip. Alfred was in hospital at the same time, having had heart attack. Cedric's gone. Willie's gone. Owen Minor's gone. Ken is still living it up, and but the others are unfortunately not doing so well. Hassel, early picture, and he does look like a Boy Scout there, doesn't he? He doesn't look like an old professor. He just finished his PhD and he's thrown in as head of department. Anyway, he wrote this and sent this to me some years ago, saying that, you know, when we started there were the three of us, and we didn't distinguish between the various sections. We all had to do a little bit of everything, and then we started to get some experts come in to try and teach in varying topics. So we had Bill Bartley come in, and then we were able to promote up our own students. So we had Bunny and Willie and Ken Stewart and people come through who were our own graduates. Joyce, who was the first secretary employed on campus, was the secretary for many years in the department. He also recognized that it wasn't enough just to do traditional pure chemistry teaching. He needed to get into applied chemistry and to be able to develop stuff for the region, and came up with the idea of running a course in chem technology. And this lasted for a few years, and then engineering was set up in Trinidad, and so the sub-department was then shut down. The office that they were using was then captured by geology, so we'll mention that a bit later. As I said, the Gleaner has been very useful in trying to find information on people and what happened to them. So here's Roger Cade in the middle of a maths or physics class. He went on to Puerto Rico, and so he had come in '48 and then had left. Francis Bowen, the physics people will know as Bobo, and they always claim, physics always claims that they were the first department, right? Because although the ads went out in July of '47, and we saw the recognition of who was being appointed in the January, here's Bobo coming in December, having arrived on the 22nd of December, before the January announcement of who's been appointed. And Bobo's already there as a member of the staff, and clearly, as he was on the ground, he was able to set up some space and get things moving for the physics department. So, I thought you would appreciate that. Right. He then disappeared for the first year. So Ken Magnus, for example, says he never really saw him the first year because he went off to finish his PhD at Imperial. So he wasn't around to do much teaching that first year that the students came in. Oh, on the side here, he was warden of the Gibraltar Hall. Here's Ken Magnus sitting here. Helen, if anybody's interested in more of the history, his Harold Drayton's 900-page book will be in the bookshop soon. Right? It's there. So Harold's just published a 900-page autobiography, including a good section of what life was like on campus, and he's only just died as well. So, Bobo in a physics class over at the Huts. He died in '71. It was interesting when he was interviewed in '47 as he was coming in. He said it was going to be his greatest pleasure to be involved with higher education, since there was virtually nothing in the West Indies. Barton was one of the early physics people as well, and he worked on cosmic radiation. A horrible picture is the best I could get out of the Gleaner with one of his master's students, and this one I found in an obituary. And so he was regarded from his obituary as one of the founders of particle astrophysics. And he's also listed as the first person to use digital recording on a scientific experiment. So there you go. That was according to his obituary. And he had done it using 8-track audio tapes to capture information. This paper down here, Barton and Reed, we'll come back and look at a little bit later on as well. Again, physics, continuing on. These numbers up in this top left indicate their position of ranking of on order of deanships. So he was dean number 7. So I've been going through physics department at the moment, so the numbers are not in sequence in terms of deans, but I'll try and point out, and so look for that top corner. This is now up on the top of the physics postgrad, and had been up in Stony Hill, and I think Ray Wright was one of the people who initiated getting this thing. This was a 10-inch telescope that used to be up, I think, at Stony Hill, and it was inside the dome. I'm reminded that there were several observatories set up prior to the Stony Hill one. The earliest, I think, going back to 1730, Colin Campbell, who was a friend of Halley's Comet fame, set up a magnificent facility in Black River. And when he died, Alexander McFarlane, who was the postmaster in Kingston, moved all the equipment down to North Street, built a house with a flat roof so he could set up all the equipment on the top there. And when he died, his brother decided to shift all the equipment up to University of Glasgow, where they named their observatory the McFarlane Observatory. A bit more recently, Harvard had an observatory in the 1930s near Mandeville, and I had got the story from somebody, and I don't know who, that one of those telescopes from Pickering had ended up at UWI. So in addition to this 12-inch, there's a 9-inch and a 20-inch, I think, around somewhere. And so maybe it was the 9-inch that had come from Pickering. Moving on to maths, Leslie, Dean number 8, had a master's from London. He was promoted in 55 and then became the first professor of maths in 65. He has the distinction of having been dean in arts and in science. I think the only person to have, maybe somebody from geography could do that, but in those days, Leslie was the only, and not simultaneously mine, but he was a dean in arts and a dean in science, and he became the first principal of the Mona campus. Ron Reed is apparently quite a character. Born in London, used to write articles for the Gleaner on caving, on maths tricks and puzzles, and he and Willie Chan decided that they were going to go off and learn Chinese. Now, Willie gave up after the first few weeks. Too difficult, right? This is Willie Chan, right? But Ron continued on and became an interpreter in the courts. right? So clearly became proficient. This I found, if you go to YouTube and look for Ron Reed String Olympics, for the British London Olympics a few years back, he came up with this idea that you could run your fingers around with this bit of string, and by pulling things through and through and through, and then this and this, you could come up with the 5-circle thing there. So check it out on YouTube. Here he is. Again, this was outside the nunnery in 1950, waiting for the installation ceremony for Princess Alice. We keep on complaining that, you know, maths is an integral part of the faculty and everybody must do some maths. This is going back to Edwin Allen, the Minister of Education, back in 1960 something or other, that clearly maths was important and had been set up, and they were trying to run courses for teachers and whatever from way back then. Ron made this our first computer, and it's called a differential analyzer, which was part of that paper that I mentioned with Barton, and he sent me this description of what it was all about, and you can probably read it faster than I can, but he made it from Meccano set pieces back in 1950-51, and it lasted for a few years. So they got this paper out of it with Barton, and then they needed some space, and so they dismantled the whole thing. But then coming up near 1960, they heard that US aid was offering to come up with some money, and so they decided that it would look good if they could show that they had this enthusiasm for computing, and so they resurrected this thing and put it all together. And he thinks that this played some part in them getting the IBM 1620, and I'll show a picture of that with Ron a little later. So Ron, and this guy went on to do the Chemtech degree. Ian Isaacs, the last I heard, was in Darwin. All right, our first postgraduate, in fact, got his PhD before we had our first graduation ceremony. All right, so the first PhD from the university came before we had any undergraduates graduating. Okay? So he came in with a master's to replace A.C. Ellington, who'd resigned at the end of the first year. So Lippmann came in as his replacement, and the thesis is only deposited in London. When I tried to get a copy for the library here, they said, "You want to put a copy of our thesis in a foreign library?" I got vexed. So I wrote to him, and he sent me a copy, which I scanned and OCR'd and stuck up on the institutional repository. Here he is outside the prelim lab with a group of the med students. He was he decided he wanted to fly a plane, so he flew out to Jamaica to come back to give some talks in the mid-50s. His thesis is there. He also sent a copy of his certificate, which doesn't mention UWI anywhere. No mention of external, no mention of, here he is, just a student of London. And of course, it meant that he had to go up to London to do the oral exam. So, when we look at, this is chemistry now, when we look at the first chemistry PhDs, we've got Lippmann at the top. Willie Chan was the first in chemistry in terms of those who had actually graduated and had come through the system. And so he came out in '56. Again, University of London is showing there, but I think it does say something about external student on his copy. When I did a quick count, we're now up to something like 130 PhDs coming out of the chemistry department, and something like over 250 altogether, research degrees, MScs and MPhils, depending on what year, which doesn't include some of the research master's courses that OSH and food processing have done. When you talk to people like Conrad Douglas over here, he'll tell you that there's no aspect of the chemical industry and research that goes on within the island and region that doesn't have some sort of impact from postgrads from chemistry. Hassel had this idea that he had to start the research going from day one, and so he published something like hundreds and hundreds of papers, but within those first few years, these papers had come out with authors from the West Indies, and even after he left, he carried up some of the students from here to continue on work at Wales, where he went to Swansea. And so people like Compton Seaforth, for example, from Trinidad, had started, I think, a master's here and went off in the middle and finished up with a PhD from Wales. All right, our first dean. All right, we got there eventually. Our first dean, right, now, was Asprey, and he came in to look after the botany department. In those days, they all gave inaugural lectures, and Asprey gave one on plant geography. Skelding took over from Asprey when he left, and again, there was a lot of interest in what was going on with the thousands of plant material that was available within the country. Many of you will have seen the book by Adams, right? Charles Dennis. I've got it written down somewhere. There it is, Charles Dennis, 1972, with input from George Proctor and R.W. Reed. And so, well supported by Skelding. Lloyd Coke was the 13th dean. And you can see lots of impact involved with SRC tissue culture, Banana Board, National Science Policy, editor of Caribbean exams, and so on. Plant biotech, he was the first academic supervisor and to have a successful MPhil in tissue culture work. George Sidrak, spent 36 years here on campus. Many of you won't recognize this beautiful looking lake, which never really looks like that. You have to get it on the right day and with the nose peg on. The new building behind there. What was interesting was this picture on the left here, a sign of the times, George smoking, Skelding smoking, Konasevich all smoking, and with a glass in the other hand, right? So things have changed. This one was a constant reminder. I sent this to George when he was leaving, because he'd been very up in arms about the number of times that goats had got in and eaten down the botany garden. And so I sent this. This is the personnel office. So I said, they're queuing up for your job, George. So the goated community, anyway. Millet, not a dean, right. And he gave his inaugural lecture on the reaction of light to the Caribbean sea egg. And it says, you reach Irving Hall from the Pepine Corner by the Lindo Gap Road. Anybody heard that name before? Lindo Gap Road. Right, I hadn't seen that before, I must admit. Anyway. Here's Millet and Underwood in the old wooden lab in the early days. Many of the students that you talk to who sat through Millet's lectures says that it was really quite remarkable to see him at work, because he'd be writing with one hand doing the diagrams and he'd be annotating with the other hand in a different colored chalk simultaneously. Right? He really was quite ambidextrous. He used to pull in for his genetics lectures information that, here's his grandchildren, but his daughters had red hair and he clearly didn't. And so it was a matter of genetics that nothing else, right? Right, you all got it. Okay, so when he moved up to London, they named one of the halls of residence at the Marine Lab after him. And his famous quote was, "I'm not particularly fond of lecturing, but you must admit I'm rather good at it." Right. So that was a millet. This was his retirement function that London people sent me. They sent me this as well. We heard mention of Tom Gorrow earlier, for those who went to the Discovery Bay session. And so Tom had made an enormous difference to what was happening up on the coral work. And when we think of impact, this one he named after Princess Alice, but you can see that it had a far greater influence in the society than just the basic coral structures, right? So he was the first to use, to be considered as a diving marine scientist. The wiki page says that he founded the laboratory in a disused urinal. Now, I find that very hard to believe, because nowhere in Jamaica would you have a urinal. You would have a toilet, but you wouldn't have a urinal, right? Anyway, so it opened just after his death. There's a stack of beautiful pictures up there on the web for Discovery Bay, but trying to find anything from Life Sciences Department is a real shock horror. You can get a tiny little something or other, and that's about the best of it. So don't ask the library. David Stephen was Dean number 5, and again another marine lab was set up, this time at Port Royal, some years before the Discovery Bay lab. And Ivan Goodbody then came in to take up some of that pressure from what was going on with work going on in the marine lab out there. Barry Wade had put up some notes about Ivan online, and there was a note in the Glean about when Ivan was first appointed. So Ivan had started his PhD, I think, thinking he was going to be working in ornithology, and then got shifted across, and so Barry makes mention of the fact that he was also very keen bird watcher and interested in what was happening with birds in the country. Of course, the faculty made a contribution of trying to keep the posterity and going by helping with MIAS to get out this CD, which had pictures of some of Ivan's thousands and thousands of slides. And this one he'd named after Porto Seco, but I think they also had other stuff named after their cats and dogs. They just had so many slides that they gave up trying to name everything. Bunny Leila, look out for a book that's supposed to be coming out later this year, entitled From Logwood to Slowpoke, which was supposed to give an indication of his life in science. Bunny was first employed at the logwood factory in Spanish Town, which in those days was probably the largest industrial complex in the Caribbean, employing hundreds of workers. So here he is as a master's student. Here he is over at ISONS with Governor General George Sidrak, Ken Magnus. Here we have his elevation, getting his honours, and here he is at home pointing up to a picture of Cedric Hassel, his mentor, and who'd got him his first job at the logwood factory. I guess in terms of faculty, one of the things that we have this huge resource on campus, the ISONS, and that has made a substantial difference to what's happening with research in the faculty as well. Bunny was involved with a thing called the Caribbean Chemistry Symposium Series, and Cedric came out and Haynes was there. Here's Bunny over here. Willie Chan, Baldwin, Sydney Martin, thank you. John Chandler, Alfred Sangster, E.V. Ellington, Ken Magnus, amongst others that you may be able to recognize in there. The series started in '61, and I think it's still continuing. It's had a little bit of a hiccup now and again. It was running every 2 years initially. I know a number of people from the department who went down for this thing in '83. I missed it, and I missed, I think, all of them so far. But so there was a number of these things that went on. I liked this one, that Bunny was the conference coordinator, the '67 meeting, and he had a whole heap of inorganic coordination chemists come out for that meeting. Morning sessions will start at 9. Who's running the faculty conference? And the morning sessions will start at 9, and we'll also have evening sessions starting at 8. But this bit, the cost of the dinner is £1. Hey! And you can use the Olympic-sized swimming pool. You know. Haynes was our second head in chemistry, and this building, Haynes, I think, was partly responsible for trying to sort out and arrange. It showed the plans that we now have the traffic right. For years we used to come in at the bottom and come out at the top, but the original diagram shows there's a car here going in at the top and coming out at the bottom. So we've now finally got the traffic sorted out correctly. The other thing that has changed substantially over the years, here's Haynes talking in a class. You can see this beautiful old box here for displaying books and so on. But on the desk in front of everybody is something for your cigarettes, your ashtray. That they've all disappeared. Willie, Dean number 9, as was mentioned, he was the first UE graduate to get a PhD. Here he is in the labs in the early days. This one took me a long while to try and figure out how you could get that photo taken from that position. Because clearly this is looking under chemistry here, and you can see that there's a number of columns there, and they clearly haven't changed those position of those columns over the last 50 years. But so the columns are still there, but this tree was what was upsetting me, because it looked like the tree was on this side, and there was no picture that I've ever seen that had a tree on that side. Anyway, I figured it out, that it's the tree that's on this side that had a big branch that came over. Anyway, this was Willie's retirement, so Alan, you're not there, but we've got a number of former staff in here: Pascoe, Vernon Box, Basil Burke, Jimmy Rawle in here, and Trevor in there as well. Willie and Cedric came out and got awards for the 50th, and here's Willie getting his CD. Willie was involved in setting up the Mona Symposium, and the first one here was talking about how we've got all these people coming out from MIT and Oxford and Yale and Bonn and Brazil, and even people coming in from Ibadan to talk about natural products and what could come out of it. We have the names of everybody, I think, here identified. That was the first. This was the 21st some years ago. That's what that looked like. This one I put in for 2 reasons. Here's Bill Bartley in the Bartley laboratory, still with the flip-flops, no shoes, even with royalty there. Right? So I thought that was really cool. The other one I liked because my first car was a Humber Hawk, and I never saw a polish that looked anything like that. But I didn't have the half a dozen people to look after it, I guess. Geography, geology now, of course, UCWI days have now finished because we're now up to, well, almost finished. Geology was established in '61, and they took over, as I said, that ChemTech building. They loved it because the alcohol was still there for a while, and so the smell really got them going and got them charged up to keep the day going. It didn't help when it rained, however, because they all got wet. They then moved across to the De La Beach building, and geography came in around about that time as well, in the 64, 65. So the first head of geology was a guy called Burke, and you'll see that he's only just recently passed on. Early papers included one with Ted and Tom Gorrow. And you'll notice as well that the journals was set up by the department as self-financing journals, things like Caribbean Geography, what's now called the Caribbean Journal of Earth Science, which went through various names over the years. Barry Floyd was the first head of geography department, and down here we say that their first postgrad started in '67, and Wilma Bailey, who was the first PhD in geography and was also the first professor of geography. Computing now, of course, we're really coming up to modern days. 76 was really when they started teaching in Comp Sci, and it had been part of what was called the User Services and Teaching section of the Computing Center, because Roy Bailey was brought in to run the IBM after the census in 71. So the government bought this big computer to do the census and then donated it to the university, and Roy had this IBM as his personal PC for many years over at the computer center. So along the way, they had a number of part-timers and people that had come through, and it wasn't until then Anne Reiskelt came in, was the first head in 91. And that reminded me, not many to go, in terms of impact on the faculty, probably one of the things that has changed the way that we operate the most has been the fact that we now all have computers and email access and internet and so on. In 1985, it said that 80 people on campus had actually used a computer terminal that year. 80 people. And it's then started to grow and grow. And when the convicts came in, a number of us said we don't want it, but if you're getting it, what you have to do is to set up fiber optic ring and get machines out to all the departments and get everybody connected. And so we got our a workstation set up in chemistry, and in '94 we got the first website in the Caribbean. In '95, this ad went out for IDB funding. I don't know if you can read it, but there were 305 computers that were supposed to be brought in at that stage in one go. Right? That's remarkable and not seen since. You're lucky if you can get 2 or 3 at a time, but the idea of 305 coming in one time was really quite fantastic. Here's Ron Reed again in the 1961 IBM computer that was purchased after everybody seeing this poor analog thing I made out of Meccano's set and took pity on us. So he was able to run that. Here's the convex arriving in '92. This maze of wires is in the back of chemistry, is now in a nice cabinet and looks a lot prettier than it did there. There's the first website, and this fella here had some hair. So I'm done. We've got a list of deans and pictures of them all. I don't know if you've been into the conference room in the faculty office. The pictures were all different sizes, so I managed to produce a set all the same size. And current office looks a little bit like this, and a little bit like this, and that's where we're looking. I should point out that another spin-off of the impact of the faculty in the region has been the Caribbean Academy of Sciences, who this year is up for its 30th anniversary. Right? And so there's a conference on campus the end of November. Abstracts are due end of June, so if you've all got posters and papers put together for this, and remembering that 50% of you didn't get a chance to present, so there must be plenty more come in. Here's the opportunity, you know, to push it. And final one, some of the pictures I managed to get from archives, some from the main library. Matthew Haynes, who was the son of Lenny Haynes, I was able to get a few from. Alfred Lippmann sent me some, and when he died, his son-in-law sent me a few more. This was one of the pictures I got from the library. Here's what I guess SLT2 now, the old Science Lecture Theatre. The E.V. Ellington Lecture Theatre would be here. The bathroom block is there, and the faculty office would be just on the other side of this. So this is where we've come from in the last 70 years. And I'm done. Thank you.
Questions, comments?
Psychology and chemistry. And at the end of the first semester, I had alpha ratings in chemistry, and then all of a sudden I got a letter from London University College offering me a place. So I marvel now in seeing that, you know, your history with London University College and Imperial College, which puts us into the same family.
You don't want to get me started on London University, because the very first professor of chemistry at London University was born in Clarendon. Right? So when putting together info for this book I did on the history of chemistry department for the 60th anniversary, and we bring in all these white men to start up all the faculty, right? Here it was that when London started in 1828, their first professor was white, but he was born in Clarendon, so we have a good Jamaican connection with the University of London.
Anyway, I won't get into the melanation.
Right.
Two of my grandfathers were white.
Yeah.
But London University College sent me on to Paris because what I was interested in, they weren't on track in England. The French were very much on track.
Yeah.
And that was molecular biology and the tissue culture and so on. What I would like to share with you is that since coming here, there's no mention of any French inputs, and yet molecular biology was not purely Watson and Crick. There were inputs, you know, by the French. And also in evolution, it wasn't purely Darwinian evolution, but also there was Lamarck. I'd advise you not to stick solely to the British histories, because given your comment, but to get in some of the French. And since my background was the Sorbonne, passed on from London, I'm saying to you, why don't you try and get on track with some of the more European things developing now? And, you know, that way would get you out of the British histories too.
I have a paper that just came out today on translators of the German Justus von Liebig, 3 with Jamaica.
Comment. Is it, from your account, geology actually started before geography, or was it that geography was in arts and migrated across?
I think geology did start a few years before, and it was 65, I think, that the teachers, I think, in schools sent their message saying we need some geography courses so that we can get our teachers up to speed. No. And most of it was taught out of arts. First female PhD. I would have to look. I don't have it in my head.
We had a discussion about the low achievement of the female graduates in the early years, and my take was that the women with science aptitude tended to go to medicine. Yeah. So you know, so I think that was it. It wasn't that necessarily. Okay, so questions, comments? If none, then we will thank Robert once again, Professor Lancashire once again. First females faculty.
Oh, well, there was Edith Robinson, and there was, if you look at that first, home. Mouse is gone. Come back, here we go. If you look there, we've got Edith Robinson was a lecturer in botany, and I think she lasted until the 70s. I think she was here for quite some time. And there was Violet, who unfortunately committed suicide a few years later. There was also Jessie Rankin, was one of the early female members of staff in zoology. I'm not sure how long she was here, but she was here for a few years as well. All right. Yeah. Behind.
Thank you very much, Prof, for the review of the last 70 years. Any thoughts on the next 20?
Well, I was saying that thankfully I won't be here to do the 140th or the 100th or the whatever. I may be lucky enough to manage the 80th, but I'm a little pessimistic, I must admit. Having been here for 40 years and seen things fluctuate, to be able to run something successfully needs some input of cash. And at the moment, I'm not seeing where that's coming from. So unless you all go out and do what Edith Sims' colleague had done and make a few millions here and there and send some of that back into campus, I'm really not sure that the government's not going to be able to put that sort of money in. So it's been a while since we've had a major push of equipment and funding into departments. I mean, I showed that picture of the early labs. And as I say, here's a student with equipment in front of him. Nowadays, the first year chemistry lab, it might be one student sharing equipment with 3 or 4 others and not getting individual equipment. And each year it gets worse as the money doesn't come in and equipment gets broken and not replaced. You know, so it is a little. Now, if we wanted to do physics with pendulums, we could do that. But you know, if you all want to give everybody a Raspberry Pi, even, you'd be hard pressed. You know, so. Yeah. Time for me to shut up.
Yeah, some housekeeping, yes.
Please give us support. And if you want to hear about the next 20 years, you have to come on Friday. Thank you so much.